Before we start example 3, I want to notice something that was present in the previous example and that we'll use in, or sorry, example 4, and that we'll use in this one. So we encountered this integral dz over z minus z naught in the previous example. And when z naught was 0, we actually had already encountered that. And I'm going to raise it to the nth power here. This is an integral that shows up again and again, so I just want to take a moment to say what it is. So what is it equal to? Well, it's equal to 2 pi I if n equals 1 and z naught is interior to c. And it equals 0 at all other points. So that it equals 2 pi I when n is 1 and z0 is interior to c, well, that's easy. You just reparameterize it like we did in the previous, you parameterize c like we did in the previous example, except for you don't do c, you do a circle of radius, of appropriate radius about z0. And the computation is exactly the same. And the fact that it's 0 away from that, well, what is the real reason? Well, the real reason is that, the integral of c of 1 over z minus z naught to the n is like the integral over c z minus z naught to the negative n, which if n is not 1, this is like a reverse power rule thing, right? It's like 1 over minus n plus 1 z minus z naught to the minus n plus 1. It's not exactly true because we haven't shown that that you can compute these with antiderivatives, but you can in this case, and this is going to be sort of the start point minus the end point, evaluated from the start point minus the end point, and that's perfectly fine to do. And when you end and begin at the same part, you're going to get 0. So when n is not 1, this is what you get. However, when n is equal to 1, you get some log as an antiderivative. And that's roughly why there's this special case when n is equal to 1. By continuity of log, you're going to introduce an argument, a period, right? A period of a certain function, and the period for the argument is 2 pi, so it repeats itself every 2 pi. But nevertheless, I just wanted to remark this. Let's start the example now. So in the example, what we're going to do is we're going to compute the integral over c of 5z plus 7 over z squared plus 2z minus 3 dz. And c is the circle of radius 2 centered at 2. All right, so how are we going to do this? Well, let's notice that z squared plus 2z minus 3 factors as z plus 3, and then z minus 1. Now, 1 is, so this is 0. Let me just note this is 0 when z equals negative 3 and z equals 1. Negative 3 is outside of the circle, and 1 is interior to that circle, right? Because circle of radius 2 centered at 2, it's going to go over to 0. Here's 4, here's 0, but negative 3 is all the way on the outside. All right, so if you remember partial fractions, which if you don't, you can look it up in any calculus book. I'm not going to do all the details here, but you can rewrite this as 3 over z minus 1 plus 2 over z plus 3 by partial fractions. All right. Then what? Well, therefore the integral over c of 5z plus 7 over z squared plus 2z minus 3 is going to be the integral over c of 3 over z minus 1 I'm missing a dz somewhere, aren't I? Plus the integral over c of 2 over z plus 3. But this guy here, this guy has no problems in that circle, right? This is analytic on and interior to c at all points, right? So when we compute this integral by the Cauchy-Gorsat theorem, that's 0 by Cauchy-Gorsat. So the only one that we actually have to compute is this first one. Let's factor out that 3. Now, by the discussion we had at the beginning of this video, this is a 1 over z minus z naught to a power. It's the power 1. And when we integrate that over a contour that contains that point, we get 2 pi I. So the value of this integral is 6 pi I, and we are done.